Good morning. I shall be today talking on toughening of ceramics. But before I take up the topic, go to the actual topic, let me say why is it important. A ceramic has, let's say there is a section of a ceramic, a very enlarged section. It has grains with different orientations, different sizes. Some of the grains may be oriented in this direction. The grains are randomly oriented. They are of different sizes. Now let us say that we are imposing a force. It is supported at this end and supported at this end. As we impose this force, what happens? First, nothing happens. And then the energy that we are giving essentially gets stored in it. However, in this microstructure, there are many flaws. There might be flaws in the grain boundaries, or rather let me use a different pen. There might be flaws in the grain boundaries. Over here, there might be flaws within the grains. All of these are flaws. Now, as I keep on increasing this load, nothing initially happens. The energy simply gets stored within the matrix. But a stage comes when the stress given reaches a critical level where the first flaw just takes over. It is just higher than the critical stress. So what happens? If this is the first flaw it comes across, it just opens up. Essentially what would happen is a crack tip would form. Now all the load is hence focused only on this crack tip, which is hardly a few angstroms. So as a result, what happens is the tremendous force over here, this crack starts propagating. It keeps on propagating and the crack proceeds. Here in this diagram, what I have is the crack started with this flaw, then starts proceeding over here. Here it encounters a grain boundary. It encounters a grain boundary here. So this is the grain boundary it has encountered. What can happen here? The propagation of the crack can stop. The crack can go around the grain boundary, which is over here. It could have taken this turn also, or it could have generated many more cracks, which again prevents the flaw from going ahead. Essentially, a ceramic body, like say you take a chalk, as you bend it, after a certain force, the chalk breaks, because there is no mechanism available to the ceramic to stop this crack propagation. However, if the ceramic is so engineered that there are inbuilt systems within the ceramic which can stop the crack from propagating, as I have done over here, then obviously the strength can be increased. Now, what are the possible mechanisms? Possible ways to increase strength. Let me first list them out and then take them one by one. One is by modulus transfer. Second will be by pre-stressing. The third will be crack deflection. The fourth, pull out. The fifth, crack shielding. And this, I would stay over here, because normally people would write energy dissipation. These are the ways I can increase the strength of a ceramic body. Now, let us take modulus transfer. Most of you use chairs which are basically plastic chairs. These plastic chairs are basically FRP, fiber reinforced plastic, and this fiber is generally a glass fiber. So, what happens over here is the glass fiber has much more higher modulus of elasticity than the plastic. For modulus transfer, this is very, very essential, that the fiber has to have a significantly higher elastic modulus than the body. So, how does it do it? Even in case the plastic chair develops a crack, the fibers which are built in to the chair inside the plastic matrix, they carry the load. Here in I have talked of plastic systems. Now, in ceramic systems, I had a few classes ago talked of SiC fiber reinforced Al2O3. Al2O3 fiber reinforced SiC matrix, while I was talking of chemical vapor infiltration. And here what happens is, in case the matrix fails, the fiber carries the maximum load, and hence the strength increases. Now, there are several factors that control degree of toughening. There are several factors. Essentially, the first one is difference in modulus between fiber and matrix. They have to be chosen in such way. 2, strength of the fibers. 3, volume fraction of fibers. And also architecture of fiber design. What I meant here was, which I had discussed during the CVI process, was I could have simply fibers oriented in one direction, or I could have fiber mats so that I have got strengthening in both the directions. The third option is so depending on how the fibers are woven, the strength or the degree of reinforcement will change. Third and fourth, obviously we are talking of length of fibers, whether they are short or long. And fifth, most importantly, interfacial bond nature between fiber and matrix. As I said the last day, while I was talking of chemical vapor infiltrated fiber mats, there the surfaces are coated with an agent so that the matrix can slide over the fibers. If the matrix and fibers are very well bonded at the interfacial level, one problem I will face is the fiber will crack along with the matrix. Rather, if the fiber can pull out, as the like say the matrix is pulling out, but the fiber is holding as I am pulling the pen out. But if it was so very well bonded that I cannot pull it out, what would have happened? The entire structure would have broken. Now, what is the effect of the elastic modulus? Obviously, the greater the difference in elastic modulus between the fiber and the matrix, the larger will be the load the fiber can carry. Now, it is a general rule of thumb that the fibers should have at least twice the strength than the matrix. That is a fundamental rule. What is the effect of volume fraction? What do I mean is, if this is a matrix, let me consider two matrices, and let us say that over here the fiber concentration or the volume percentage is lower, whereas here the volume percentage is much higher. volume percentage is much higher. So, it is obvious that this material would be much stronger than this. Let us say that a case where I have taken silicon carbide in aluminum matrix. Does not worry about the fiber diameter and all of that. Here the strength of matrix is less than 75 megapascals. If 30 volume percent of SiC is added to the aluminum matrix, the strength would shoot to around 600 MPa. That is, by from 75 MPa strength of the aluminum matrix, we increase the strength to as much as 600 MPa just by adding 30 volume percent of silicon carbide fibers. However, one thing is very important, that yes, higher volume fraction of fiber reinforcement is essential to increase the strength, but it is also very essential that the fibers do not entangle with each other. They are simply free and they are placed at the proper distance, because if they start entangling, then what would happen is the strength would be totally lost and the effect on the composite would be very deleterious. So, I had talked of modulus transfer, and this is how it is done. The next one is pre-stressing. Now, this is obviously many of you have seen pre-stressed concrete. What do? They have this box where they will lay the concrete over here. The fiber, the aluminum, the iron rods go across. First, the iron rods are pulled. In this direction, this one is pulled in this direction. What happens? The rods come under tensile load, stretching. Then the concrete is poured in. And allowed to cure. What happens now? After curing, the pulling pressure, they are released. The rod tends to go back, shrink, go back to its original state. But because it is embedded with the concrete, it imposes a compressive stress. It imposes a compressive stress. What does this compressive stress do? As I had drawn earlier, this is a flaw. This is a flaw that is propagating. If there is compressive stress, this propagation is stopped. because because it's something like this. The flaw is proceeding, but then if there is compressive stress, what would happen? The flaw would force to be closed, and as a result, further propagation of the fracture is stopped. Now, you have seen this pre-stressed concrete example, and even if you have not seen, if you could care to look at the construction sites around you, you would realize how pre-stressing is done. Here, in case of pre-stressing, tensile fracture will occur only if a huge load is applied which exceeds the compressive load, and that is a huge number, very large number, and so they cannot initiate the crack flaw. The crack flaw is self-sealing. Another way in which strengthening can be done is simply by surface compression or quenching. Is by surface compression or by quenching. Today, the spectacles I am wearing is a glass one. It is not the spectacle I wear every day. And this spectacle is hardened. I can throw this spectacle right across the wall with all my force, and the glass will not break. How was it hardened? There are two ways. One, there are three ways. Heat the glass, equilibrate, and then suddenly hit the glass with a blast of cold air. You see, when this glass is heated, it expanded. Now, all that they did was, after heating it to about 350 degrees centigrade, they take this glass out and blast it with cold air. Then, when they are blasting with cold air, the surfaces will get cold faster. And as a result, what will happen is, because the surfaces contract faster, they would impose compressive load on glass. So, if there is a compressive load on this glass, again what would happen is, for the flaw to initiate and propagate, the compressive forces force the flaw to join together. Another way is ion exchange. The same thing can be done, that is, it is immersed in a molten salt bath of, say, KCl. What happens is this: if this is a glass surface, there are sodium ions inside. The potassium ions migrate and sit on the surface, and as a result, the potassium ion being larger than the sodium ion, it would impose a compressive force. And the same thing would happen because of the compressive force. The glass, the fracture or the flaw would again close before it can propagate. However, it is true that once, in this case, if this is a surface hardened glass, which the surface has been hardened, once the crack gets in, what happens is, what do you see when the car windows get smashed? The fracture propagates in every direction, creating cracks, subcracks, microcracks and everything, and for stress relief. This you have seen in many automobile accident cases where the glass has been blown to smithereens because it was a toughened glass. However, I believe that Suzuki has of late come up with a toughening mechanism of the automobile glass which would prevent it from cracking and retaining its position, which is a major problem of glasses. The cracks would get in and propagate randomly. I have already talked of, so essentially I have talked of compression, stressing, I have talked of surface, pre-stressing, that is the ion exchange and anything, all of that. The third one is caused by difference in thermal expansion coefficient between fiber and matrix. If there is a difference in thermal expansion coefficient between the fiber and the matrix, what happens is that the fiber expands, contracts more, and as a result the whole thing goes into compression. So all of these are basically going into compression molding, that is a pre-stressing what I had talked of. Another way of inducing surface compression is what we call layering. Now, this is an esoteric technique, not really in use in the industry, but it has tremendous potentialities. That is, if this is a ceramic body, we deposit on it a second material which has a different thermal expansion coefficient. On top of this, we deposit a third material on top of the second material. Now, this can induce a huge compressive stress on the body during the cooling. One very good example of this layering process is the coral dishes, which are unbreakable, and I did talk of them when I had talked of about these in the earlier parts of the course. This is also a compression technique. Next, we have crack deflection. That is something very easy. For example, in concrete, you have stone chips, you have 2 if not 3 grades of sand, coarse, medium, fine, and each of them can deflect a crack. And that is how basically concrete is made stronger, by putting in these materials. This crack deflection or impediment in engineering ceramics is what has been used heavily by the industry. So, here what happens is, if this is a ceramic matrix, if this is something that we have deliberately added over there, then as the crack initiates, it comes and stops at this particular point. If it has to go across, if the force being applied is huge, then the crack has to deflect right across and then proceed. So, this is the extra amount of energy or load that must be added to the initial load before the crack can proceed. A very good example of such materials are, for example, glass ceramics. Where here you can see that the crack has been impeded. These are different crystals inside the glass. The crack has to go, it has to break across these crystals, follow the grain boundaries, break these crystals. For example, here it has to fracture the crystal, it has to break the crystal here, spend huge amounts of energy before it can proceed. I shall take up this glass ceramics later, possibly today. Now, if you saw there a huge number of ceramics of the ceramized glass in the glass matrix. Now, if the amount of the ceramized glass in the glass matrix was small, crack propagation would have been easier, the material would have a smaller load bearing strength. But as the number of impediments increase, the more the number of this crack deflection, and hence the strength of the material increases. Most of this crack deflection technique has been centered around by trying to add in the ceramics different sizes of second phases, single size, multi size, different sizes, so the cracks get deflected. What happens is, normally it's not one crack which happens, there is another crack which propagates. Frequently the cracks impinge on each other and thus prevent more cracks. If you have seen old porcelain cups at home, you will see that the surface is heavily cracked, but with very fine micro cracks. That has happened because the surface flaws were there, they cracked, but then they interacted, and as a result many more tiny micro cracks were formed. Now, each of these tiny micro cracks is going to prevent further propagation of further cracks. So, here crack deflection can occur by a particle, crack deflection can occur due to interaction with a crack, crack deflection can occur by interaction with micro cracks. But whatever it is, whether it is a particle, whether it is a crystal, whether it is a crack or a micro crack, the more energy has to be spent for the crack to bend around it and then go. And this leads to significant increase in strength of the ceramic body. Further, what happens normally is this, that when we are dispersing one material in another, the hardness increases, abrasion resistance increases also, but that is not what we would be looking for. Another thing that works is, let's say over here, as a crack propagates, what will happen? These will also have to be pulled out. The crack would stress these fibers, forcing them to undergo necking. Now, here please understand, I have drawn on a very exaggerated scale. So, as the crack tries to proceed, the fibers are also elongated, and hence now the crack not only has to bend around the deflection, but it also has to have sufficient energy to proceed, because as it proceeds the fibers will elongate, and that will increase the strength of the material, and this way the fracture toughness will shoot up very fast. Now, as a continuation of this, I come to pull out. Pull out means in these matrices, if the crack has to proceed, the fibers have to be pulled out of the matrix. Pulling out means the fiber has to debond from the matrix, for which energy is again needed, and this requires more force to debond the fibers from the matrix so that a pull out happens. And this pull out mechanism is one of the reasons of strengthening of most of the fiber reinforced ceramics. The next one is crack shielding. You see, let me put it this way very simply, very easily. You are seeing the tip of the pen. I would ask them to, yes, focus on the pen. Now, if what happens is there is a pressure at this point, as there is a compressive load, this load is going to be transferred to the pen. Now, at this pressure, what is if happens like this, this is the tip, this is the force is increasing. Under such conditions, as the force increases, if phase change can occur, phase change can occur. Now, whenever there is a phase change, it is obvious that energy will have to be supplied, and hence if the crack comes up against this, firstly there is deflection, no doubt, but then not only deflection, if this particular grain undergoes a phase change, then crack propagation will require more energy, and hence this phase change will prevent the crack from propagating. Now, this is what is crack shielding. You see, this energy dissipation, the last one, it is really a summation of all these processes. Modulus transfer, pre-stressing, all of this are requiring forcing the putting in more and more energy so that the material, the crack can propagate. So, the energy dissipation, which is the last point I had written, really involves crack deflection, pull out, crack shielding, pre-stressing, modulus transfer, and all of that. Well, we have dealt with the fundamentals of toughening. Now, let us take up certain examples of toughened ceramics. For example, let me say Very simple example. Self-reinforced silicon nitride. Now you see, silicon nitride is one of the target materials for high temperature ceramic engines, so that the fuel efficiency of cars can increase presently from the measly 15% to 85%. So people have been working on silicon nitride, silicon carbide, trying to improve its mechanical property. Now let's take, what do I mean by over here? Let's say I have sintered silicon nitride with, I'll choose a few examples. Let me say 1Al2O3, 5 cerium oxide at about 1800 to 2000 degrees C. The flexural strength and the fracture toughness this is MPa megapascals and flexural strength is megapascals. If I sinter it with these additives, alumina, 5 cerium oxide, the flexural strength would be around 650 MPa and the fracture toughness would be around 9.0. You see, this has significantly increased. If I use something else, let me take the case of Y2O3, MgO, CaO. If I had taken this, then the flexural strength would have been 900 megapascals, while the fracture toughness would be anywhere between 10 to 14. Or rather, it will be 10 over here, it cannot be that, it is roughly 10. Whereas, if I had taken yttrium oxide, magnesia oxide, zirconia and had hot pressed it, the values would have been 900 megapascal, 10 to the power 10 to 14 fracture toughness. But if instead of hot pressing I had merely sintered, the values would drop and this is what I would get. So here what is happening is, during the sintering with these additives, second phases are being generated inside the silicon nitride matrix, and as a result all the things, modulus transfer, crack deflection, crack shielding, energy dissipation, all of the factors are happening, due to which the fracture toughness changes in this fashion. There are various examples of such toughening, that is, there is self reinforced zirconium carbide, there is I would say this is the best example of self-reinforced zirconium carbide. Now, before we go into the intermission, it's a 55-minute class, so I have to stop properly, something which I have not done uniformly. I'll come back to talk of transformation, toughened, zirconium dioxide. Let me say why is it important. Today we are going into harder and harder materials. Let's say take the case of say some of you may be pacifists may get angry, the nuclear bombs. First, inside a primary explosion takes place which releases a huge number of neutrons. These trigger the secondary one, which is the actual bomb. Now, the whole thing has to be contained, so it requires a steel which is very strong. Our cutting tools, which were made of say tungsten carbide or so, are at times inadequate to machine these steels because they are so hard. At times we need to machine ceramics also after finishing, after fabrication. Zirconia offers a way out because it can be transformation toughened, so that we can have zirconia as a cutting tool for lathe operations to cut and shape very, very hard metals like say nuclear grade steel, ceramics itself, and hence this transformation toughened zirconia is of huge technical importance. This is what I shall take up after the intermission. Thank you.